A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the infinitesimal deformation theory. So let us get started. So the topics for today's lecture will be as follows. We will start with a discussion on small deformations. We'll learn how to quantify the idea of small deformations. And then we will define an infinitesimal strain tensor that is of interest when we're talking about small or infinitesimal deformations. And once we have defined this epsilon, then we will talk about the physical or geometrical interpretation of the diagonal terms of epsilon. So let us get started with a discussion on one of the most important topics in kinematics, that is on infinitesimal deformation theory. So in the last lecture, we had defined two strain tensors. One was the Lagrangian finite strain tensor and the other was the Eulerian finite strain tensor. And we also defined these strain tensors in terms of displacement gradients. So let us start with the expression of the Lagrangian finite strain tensor in terms of the displacement gradients. So this is how we had expressed the Lagrangian finite strain tensor. And in this strain tensor, U capital A comma B is basically del UA upon del capital XB. And similarly, if I expand the other terms to clarify the gradient, this becomes like this. And similarly, we had expressed the Eulerian finite strain tensor as. So before we do anything to this tensor, let us understand what is the meaning of displacement gradients. So we have a point P in this reference configuration, or let's say the undeformed configuration. And then we have a deformed configuration where the point P after deformation becomes small p. So capital XA is the position coordinate of capital P, that is in the undeformed configuration. And the same particle small p has a position coordinate which is small xp in the deformed configuration. And the displacement of the material particle P is denoted using the u vector with a superscript P to denote the displacement of the particle P. And then we said that we are interested in what's happening around a material particle, that is capital P in this case. So for that, we defined a particle Q. I'm exaggerating things here. Q is supposed to be quite close to P because we're talking about deformation around P. And this vector from P to Q is denoted by D capital X. And then we have a small q as well, which is the point Q in the deformed configuration. And this vector from small p to small q is the d small x vector. And the displacement of q is written as uq. So if I look at the vectors here, I can clearly see that d capital X when added to uq is the same as up plus d small x. You can clearly see that that takes us from the capital P point to the small q point. This is simply vector addition. So from here I can see that my uq minus up, that is the difference in the displacements of the particle q and p, is given as the difference between d small x and d capital X. And you may remember that small x minus capital X was u, that is the definition of the displacement. So this is simply du, and that is called a differential displacement. And that makes sense because particle P gets displaced with a displacement of up, and particle Q, which is around the particle P, gets displaced by a displacement which is infinitesimally more than the displacement of particle P. So that is that u of Q is u of P plus some du. Because q is around p, so p gets displaced by up, and q gets displaced by a small displacement added to it. So du is d small x minus d capital X. And if I want to see this vectorially, I can easily do that. I simply have to draw the capital X vector starting from the point small p in the deformed configuration, which is basically parallel to the vector that I had in the undeformed configuration here. And now we can clearly see that this is the pink part is the differential displacement. I just want to give you a pictorial feel of this differential displacement because we'll be talking about it a lot in this lecture. Right, so coming back, what we're trying to understand is the meaning of the quantity del ui, let's say by del capital X A. So capital X is the material coordinates and X sub A is basically a component in the material coordinate. So let us say we try to understand this in terms of capital X1. So in that case, we have a del ui upon del capital X1. Now X1 is a direction. If I draw from the point P, it's like this. So what this means is that I find a point Q in this direction. So I choose a point Q, let's say here, I call this my Q for this discussion here. So this is what I'm talking here. And then as I move in the x1 direction in the material coordinate to find a point Q, I try to find the differential displacement by finding the small q in the deformed configuration. So whatever we did earlier to find this differential displacement du is the same thing we do, except that point Q, capital Q, has been found out by moving in the x1 direction in the undeformed configuration. So this is the meaning of del ui by del capital X1. Now ui is just one component. So if you have a differential displacement du, you just find the component of that and that becomes del ui by del capital X1. Similarly, if you're talking about del ui by del capital X2, we go in the x2 direction, find a point Q, and then do the same thing. We find a small q in the deformed configuration and get the differential displacement du and get its component, and then we basically have to divide this du with the dx1 or dx2 or whatever component we have. So this is basically going from point P to point Q here, and this is our d capital X vector. So this del ui by del xa is the ratio of the differential displacement as the deformation happens to the distance between points P and Q in the undeformed configuration. In fact, let us write the complete displacement gradient tensor. So this is the displacement gradient tensor, and you can see that the terms here are basically the terms that we just discussed in our previous discussion. So now, given that we have a feel of the different terms in this displacement gradient tensor, we'll make a statement here that there are situations where these terms are small. So when I say small, I mean they are much smaller than 1. So if the terms of the displacement gradient tensor, that is the terms del ui by del capital Xa, are small, that is, they are much less than 1, then we can clearly see that if I take a product of any two terms in this tensor, that is, if I take the product of, let's say, ui comma a and ui comma b, then this is going to be much less than u a comma b. Now I and a are just indices here. Don't get confused. They are simply indices, except that when we have a capital index after the comma, that means it's a differentiation with respect to capital X's, which is what we have shown in the tensor above. So with this idea that if these terms are small, we can write the Lagrangian finite strain tensor as an approximation to UA comma B plus UB comma A. And the term which had product of two U's will be neglected because that is much smaller than the terms that I have written on the right hand side here. And with the same idea, I can also write the Eulerian strain tensor approximately as Ui comma j plus Uj comma I. And these terms are called the linearized Lagrangian, or in the second case, it's called linearized Eulerian strain tensors. Now you will notice two things. One, that we have written linearized, and the other is that we have not written finite now. Earlier we were calling the tensor EAB as the Lagrangian finite strain tensor, but this time we don't have the word finite. And that is because the deformation or the displacement gradients this time are infinitesimal. So we very comfortably wrote that these terms of the displacement gradient tensor are small. But under what condition are they small? So these terms are small if, for example, this is your undeformed configuration, and then you take the deformed configuration, which is a slight change in the undeformed configuration. So it is as if you measured it after an infinitesimal time. So the deformed configuration then would look just a slight change from the undeformed configuration. This is the deformed, and the black one is the undeformed. There's an infinitesimal change between the two configurations. So the deformation in this case is infinitesimal. It's a very slight deformation. And when the deformations are infinitesimal, that means the displacements are really small and the displacement gradients are also very, very small. And that is the reason we write this displacement gradient as small for these infinitesimal deformations. So this clarifies the point that we did not write the word finite because they're actually infinitesimal deformations. Now the other word was linearized. So we go back and have a look at the definition of the Lagrangian finite strain tensor. So we had these two terms, and then we had a product term as well. And this product term is the term which brings nonlinearity here because it's a product of two gradients of u. So typically, we try to solve this equation for the displacements. So what we have here is we have u a comma b plus u b comma a plus a nonlinear term equals twice EAB. So if EABs are known, you'll want to find the displacements by solving this differential equation. But if you have a nonlinear term here, it makes the life very difficult. So that is the reason we study things in the infinitesimal deformation theory, where we take the deformations as really small and then we neglect this term, and that helps us with solving the differential equation comfortably. So from now onwards, we will always be talking about infinitesimal deformations, and it's a point worth writing. And by the way, if you want to talk about a finite deformation, we think of it as a lot of infinitesimal deformations. It is like integration. You integrate infinitesimal quantities to get something finite. So let us look at another property of this displacement gradient tensor that we're talking about. So if I write del ui by del capital XA, and this ui if it is expressed in the Eulerian expression, so this will become del ui by del small xk times del small xk upon del capital X a, because u is a function of small x's in the way it's expressed in this situation. Now let's recall again that displacement was given as small x minus capital X. So small x can be written as displacement plus capital X. If I write this in the initial notation, this becomes small xk is uk plus capital Xk. And now if I differentiate small xk with capital Xa to get small xk comma a, that becomes uk comma a plus capital X k comma a. But capital X k comma a is del capital Xk by del capital Xa, which simply is the Kronecker delta Ka. So if I use this here, so this becomes del ui by del small xk times del uk by del capital Xa plus a delta Ka. We open the brackets now. So I'll use u I comma k, the common notation now, and then you have a u k comma a plus ui comma k times delta Ka. Now we see that this is a product of two displacement gradients, and this just has one. So when I add a very small quantity to a small quantity, that approximately is equal to ui comma k delta Ka, which can be written as del ui by del small x. We had a k earlier, but now there's a delta Ka, so this becomes del small x a. I'll write the left hand side as well. This was del ui by del capital Xa. And there's approximately equal to sign here because we neglected the second order terms. And again, remember that I and A are simply indices. So they take values 1, 2, and 3. So this tells us that for small displacement gradients, it does not matter whether we differentiate the displacement with respect to the material coordinates or the spatial coordinates. This actually is a very important point. So let us try to understand this graphically. Now we had understood the meaning of this term del ui by del Xa, which basically meant that if you have an undeformed configuration and you find a q, which is, let's say, along the x1 direction, you try to find out the ratio of delta ui to delta x1. So the displacement gradients are finding the ratio of this delta ui to the delta x1, delta x2, or delta x3. That is, you move from the material point P to a point Q in the respective direction in the undeformed configuration. On the other hand, if I am talking about del ui by del small xj, that would mean that if I have the deformed configuration and I have a point P, I find a Q, let's say I'm talking about del small x1. So I find a small q in the deformed configuration, and then I look for the corresponding q in the undeformed configuration. So this time we are moving in the deformed configuration and then finding the inverse map in the undeformed configuration, and then we'll find the ratio of this delta ui to delta small x j. And principally these are two different things, because in one case we move in the undeformed configuration and then find the ratio of the displacement to the length of the vector in the undeformed configuration. And in the other case, we move in the deformed configuration and then do a similar thing. But under the condition that the deformations are infinitesimal, that is, the displacement gradients are very, very small, under that condition, the two gradients are approximately equal. So let us use this idea in our definition of the Lagrangian strain tensor, or the Lagrangian infinitesimal strain tensor. So this was UA comma B plus UB comma A. We didn't have the third term because we've neglected that. So this can be written as del UA by del capital XB plus del UB by del capital XA. And with what we have discussed right now, this can be written as del UA by del small xb plus del UB by del small xa. Now you see that I cannot use this notation a comma b now because that only corresponds to this situation. But now I have a small x with a capital index, which is completely allowed because index can only take values 1, 2, and 3. So I have to write it in the complete expanded form. Or what I can do is, I can write this as del ui by del xj and then multiply this by delta ia and delta jb, because then this can be written as ui comma j without any confusion. And the second term can be written as u j comma I times delta jb delta ia. And what is this? This is ui comma j plus uj comma I times delta ia delta jb, which if you recall was twice the linearized Eulerian strain tensor or the Eulerian infinitesimal strain tensor. So we have shown that the Lagrangian strain tensor is the same as the Eulerian strain tensor in the situation when the displacement gradients are small or when we're talking about infinitesimal deformations. And that's a good thing because now we don't have to work with two separate strain tensors. We'll only work with one and we'll give it a name. We will call it epsilon, which will be called the infinitesimal strain tensor. And this will be defined as epsilon ij is del ui by del small xj plus del uj by del small xi. Again, you can also write this as del ui by del capital Xj plus del uj by del capital Xi. You can use whatever form you want. Typically, we'll be using this one for our discussions. So this is great. We have been able to define the strain tensor epsilon, since we said that we'll be working with only the infinitesimal deformations. So we'll only be working with this infinitesimal strain tensor epsilon ij. This epsilon ij is symmetric. You can check from the definition. And of course, it is real valued as well from the definition of epsilon. So with this idea, the idea of principal values and principal directions, which we had found for real valued symmetric tensors, will work for epsilon as well. In fact, I'll box this because it is very important you remember the definition of epsilon. There are many cases where we'll get confused, so we'll have to come back to the definition of what epsilon is. So what we do now is that we understand the physical meaning of the different terms of epsilon. Because remember, we haven't discussed about the terms of epsilon yet. We had defined it in a finite way last time by writing epsilon as half of f transpose f minus identity, or as we've defined it today as ui comma j plus uj comma I upon 2. We did understand what is the meaning of the situation where E is 0, or now we can say when epsilon is 0. So that basically means that we're talking about a pure rotation, and we established an understanding that epsilon contains information about deformations, that is, about stretching and about shearing. But we still do not understand the different terms of epsilon. So this will be the topic for the discussion now, where we'll try to understand the meaning of different terms of epsilon. So recall from the last lecture that the difference between the square of the lengths in the deformed and the undeformed configurations was expressed in terms of the strain tensor like this. We can write the left hand side as d small x plus d capital X times d small x minus d capital X, and I'll divide by d capital X squared on both sides. So this becomes twice epsilon ij times d capital Xi upon d capital X magnitude times d capital Xj upon d capital X magnitude. Now we're talking about small deformations. So the sum of d small x and d capital X is approximately twice of d capital X. So if I divide that by d capital X, I will get a 2 approximately here. Now on the right hand side, we have twice epsilon ij. And if I look at this quantity, d capital Xi by d capital X, this basically is dividing a vector by its magnitude, because d capital Xi is a vector. So this is Ni and this is Nj, where n vector is simply a unit vector in the direction of d capital X. Now d capital X is the vector from capital P to capital Q in our undeformed configuration. So remember, we had chosen Q arbitrarily, so this vector is d capital X, and n hat simply becomes the unit normal in that direction. So n hat will help us identify the direction of a line element that we choose to understand its deformation. And now we see that this 2 cancels with this 2, and this was the reason we had defined epsilon with a 2 factor. So instead of choosing epsilon as f transpose f minus I, we had chosen twice of epsilon as f transpose f minus I, and so on. So this was just done for this situation where we can cancel this 2. So finally, I can write d small x minus d capital X upon d capital X is epsilon ij, ni, nj, and this in the symbolic notation can be written as n hat dotted with an epsilon tensor dotted with an n hat. So this quantity here is the change in length per unit length capital Dx in the undeformed configuration, because we're talking about the length in the undeformed configuration, the denominator, and this is in the n hat direction. So if you have the undeformed configuration and this is P and this is Q, so this vector is d capital X and a unit vector in this direction is n hat. So the n hat vector will help us identify where have we taken the point Q. And this is what our intuitive understanding of strain has been. Remember, in high school we used to write strain as change in length upon unit length. So this is exactly what we were discussing till now. So this is another scalar measure of deformation. Epsilon is a tensor, but for understanding more intuitive or measurable quantities, we talk about some scalar measures, and this is one of those scalar quantities that we can measure. a scalar measure. There can be others as well. So we have a point P where we're talking about deformations, or where we are defining the strain tensor, or in the neighborhood of which we're interested to quantify deformation. And then we find a point Q by taking an n hat direction, and then once we have that element in the n hat direction, we quantify the ratio of the change in length of that element due to deformation upon the initial length of that element. And this quantity has a name. This quantity is called the longitudinal strain, or sometimes called the normal strain. It is denoted with an E n hat. So now we are ready to understand the terms of epsilon. Let us see what happens when n hat is equal to I1 hat. So n hat can be any direction starting from the point P, but we are choosing a particular one, which is I1 hat. Then the longitudinal strain E in the I1 hat direction becomes I1 hat dotted with an epsilon dotted with an I1 hat. And this is simply epsilon 1 1. And similarly, we can see that E I2 hat is epsilon 2 2, and E I3 hat is epsilon 3 3. So if this is the point P, which deforms to this point P here, and if we take a point Q like this, which is in the, let's say in this case, the x2 direction, this results in, let's say, this Q, and this is your d small x vector, this is d capital X. Then epsilon 2 2 in this case is the longitudinal strain in this element PQ. Similarly, if I take a point R, so that PR is our element, in this case in the x3 direction, then if the image of this R is this R, then the longitudinal strain in the element PR is epsilon 3 3. So the diagonal terms of epsilon denote the normal or the longitudinal strains in coordinate directions. So epsilon 1 1, epsilon 2 2, and epsilon 3 3 are longitudinal strains in the coordinate directions. So now we understand the diagonal terms of epsilon. So we will end this lecture today now, and further discussion on the interpretation of the off-diagonal terms will follow in the next lecture. So today we talked about small deformations or infinitesimal deformations. We learned how these deformations are linked to the displacement gradient tensor, and then we linked our finite strain tensors, that is the Lagrangian and the Eulerian ones, to a single strain tensor, which is called the infinitesimal strain tensor epsilon. It is this strain tensor that we mostly will be working with in this course. This idea of small deformations or linearized strain theory is very important because it helps us solve the equations of displacements much easily, as working with linearity is much easier in mathematics. So thank you very much, and I will see you in the next lecture for the interpretation of the off-diagonal terms of epsilon.